Hey everybody, how's it going? In this video, I'm going to be discussing the question, fruit into baskets. You have a row of trees. You are given an integer array of fruits where fruit I is the type of fruit the ith tree produces. You start at any tree of your choice, then repeatedly perform the following steps. Add one piece of fruit from this tree to your basket. If you cannot, then stop. Step number 2, move to the next tree to the right of the current tree. If there is no tree, to the right, stop. Okay, note that you do not have any choice after the initial choice of starting tree. You must perform step 1, then step 2, then back to step 1, then step 2, and so on and so on. You have 2 baskets, and each basket can carry any quantity of fruit, but you want each basket to only carry one type of fruit each. What this means is we have a constraint of only 2 types of fruit that we can collect within a contiguous period. So the contiguous part, I deduced it from here, and the 2 types is from here. What is the total amount of fruit you can collect with this procedure? Okay, so let's look at the examples because all of this is just quite poorly phrased. So example number 1, but really example number 2 is the one that's going to hit it home. So we're just going to take these first 2 examples and you can read the third one on your own. So fruits, in this array, we have 1, 2, and 1. There are 2 fruits of type 1 and only 1 fruit of type 2. So we can collect in total 3 fruits, right? Okay, now the next one. We have 0, 1, 2, 2. The output here is 3 and not 4. And the reason for that is because if we take the entire array, then there are more than 2 types. There is 1, 2, and 3 types, okay? And what you want is something that is contiguous and something that has less than 2. So from 1 to 2, this fits the bill perfectly. As you can see, the answer here is we can collect blah, 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 etc., etc. So really, what we really need to cater for here is that we have a contiguous, and by contiguous I mean after each other, subarray that only has at most 2 different types of fruit. And mind you, 1 is not a value, it's just simply a type of fruit. This is not ordinal, this is nominal, okay? So, since we have a problem that requires us to cater for the contiguous aspect, I would recommend the sliding window technique, where basically we have a window. So let's take this right here and copy this. And we have 0, 1, and 2, and 2. And what we want to do is expand the window and then shrink it as soon as we hit more than 2 types of fruit, 2 types of fruit, okay? So basically we will go like this, 0, 1, 2, oops, what's going on here? There is more than 2 types of fruit. Then we would go back and then delete this part. We wouldn't be really going back because there would be a pointer to it, but we'll see all that in the walkthrough of the code. Okay, so first things first, window start is going to be equal to 0, and the longest, what do they call it here? Total amount of fruit. The longest window size. This is going to be representing the total amount of fruit. So this part is what we're going to return. Okay, this is the integer that we're going to return. We're going to initialize that as 0, and then we are, in order to keep track of all these different fruits and the different types and their quantities, I'm going to create a hash map, and I'm going to call it fruit frequency. Okay. Okay. Now that we have all our variables ready, let's start into the meat of the code, really. Instead of I'm just going to write window end. And the reason I'm writing that, it's because it's more expressive, because this describes the end of the window and this describes the start of the window. In range len, and then fruits. Okay, let's get the current fruit. The current fruit is going to be equal to fruits and then cur fruits. Okay. Oh, pardon me. Indirect. So that's going to be the current fruit. Okay. And then what we're going to do here is basically check if that current fruit is in fact in the fruit frequency map. And I keep saying map, it's because it's a hash map. I know some of you are Python specialists and you think it's dictionaries. It is, but it's a hash map, So fruit frequency, if it's not in the fruit frequency map, then the fruit frequency is going to be equal to 0, because now we're initializing it. And either way, we are just going to add 1 to it. Okay, cur underscore fruit plus equal to 1. So you see what we're doing here in this part. We are building our fruit map, fruit frequency map. Okay, this is a important part of our code. We're going to use it throughout. If you don't understand it, take a minute. It shouldn't be that hard. This exception here, this if, is just in case we've never encountered it before and we just want to fix that. Okay? Anyway. So now that we're expanding, right, with the window, we want to shrink it. So we want to shrink the window. We do that only if there is more than 2 types of fruits. So while, and the reason it's while not if is because I can keep on shrinking, right? If I do if, I'm just going to shrink it once, but I want to keep on shrinking as long as I need to shrink. Okay, so while the length of the frequency map, the fruit map I mean, is larger than 2, because we only specified 2 buckets. Then what I'm going to do is I'm going to take that left char. By left char I mean when you remember when I did this 0, 1, 2, 2, that one right here. So for example, if our window end, this one, is right here, then our left char is probably here. Okay, so our left char is going to be equal to fruits window start, the start of the window, right? If the left underscore char, by char I mean character, is in the frequency map, fruit frequency, then all I have to do is simply subtract it, decrement it from the frequency map, right? Then we remove this. So once we remove this, we have to decrement it, right? But here's the thing, right? Once I remove it and it's 0, I have to remove it completely. And the way I do that is through the delete keyword. Let me show you. So if fruit frequency left underscore char is equal to 0, then what I do is delete that entry entirely, right? There we go. Okay. And now since all of that is over, really, I'm just going to simply move the window start a step further. Okay? And this is the shrinking process. Once I was done expanding and done shrinking, now what I need to do is to calculate really how many fruits do I have in my window. So I'm just going to write window size is equal to window end minus window start plus 1. The reason I added plus 1 is because this is not an index, this is a length. And finally, I'm going to update my longest. By longest, I mean the longest subarray, which represents the longest, the total amount of fruit you can collect with this procedure. So max longest and window underscore size. After everything's done, I'm going to return the longest. This should be fine. I think I made a typo somewhere, but that is in essence the idea. Oh, there we go. Did I make a mistake somewhere? Nope, it works quite fine. That's it. That's the fruits in basket for you. So I'll leave a link in the description for this question. It's a very interesting question. It helps you really understand how the sliding window concept works. And I suggest you try this on your own. It's a very important question, and it could come in your next interview. We're going to be solving a problem called the maximum subarray question. This is a very popular question, and there is a really nice technique called Cadane's algorithm, and we're going to be going over it because it provides a really good time complexity and space complexity for this problem. It makes things much easier, and it's very elegant and very neat. Now, let's look at what the question is asking of us. So, given an integer array called nums, find the contiguous subarray containing at least one number, which has the largest sum, and return that sum. Okay, so for example, here you have an array of numbers ranging between -2 and -5 and 4. Okay, so -1, 2, 3, etc., etc. And the highest possible sum is 6. Why is that? Because 4, -1, 2, and 1 produce 6. Notice that they are contiguous. So he didn't omit -1 here and settle for 7. No, he chose 6 because they have to be contiguous. Now, the idea of Cadane's algorithm, it basically compares over and over again. So it compares the current sum with the current number. So, in fact, let me rephrase that. It compares the current sum plus the current number with simply the current number. Now, why is that? Because, for example, in this case here, let's think about this, okay? 1 and -3. Is that bigger or smaller than simply -3? Well, in that case, 1 plus -3 is larger. But if we have two numbers after each other that are -5 and -6, well, in that case, well, I'm going to take the -6 rather than the -5 plus the -6 because that's -11. So it wouldn't make any sense. Okay, if you find this confusing, I think you're going to understand it through code better. Okay, so we're going to have a variable here called current sum. This is going to be tracking the running sum. I'm going to make that equal to 0. We're going to have the best sum. I'm going to also make that equal to 0. Okay, we're going to loop through the numbers for I in range len of nums. Okay, we're going to get the maximum possible running sum through simply just passing the current sum plus the current number, so nums I. So the previous number, which is 0, plus the current number, which is -2. And then we're going to do that over and over and over again, right? But we're going to compare that not to the current sum, but simply to the nums I alone, to the current number alone, right? You see what's happening here? What's happening here is basically asking a question. Should I go on adding in contiguous fashion, or should I just cut off and start from the next number? That's what's going on here in the current sum. Now, when we move on to the best sum, that's what you'd expect. You'd have the current sum, which is the previous one, compared against the best sum. So this one at the top is the running, and this one is the overall best. Okay? Once that's done, we simply gonna return the best underscore sum. Now let's run that code. Well, it looks like everything's working. However, there was something that we didn't consider. We didn't consider the fact that there might be negative numbers inside our array. So having this number here 0 compared against something like -1 will always yield the maximum number as 0. And that's not something we want because that will just mess up the whole logic. So instead, what we can do, we can make a little nice trick here, which is basically, instead of best sum equal to 0, we're just simply going to make that equal to the first number in the nums array. So let's do that. We're going to make them both that way. And we're just going to start from the second number. Now let's do that. Let's run the code. Nothing's changed. Let's submit it. Brilliant. You can see here that the code runs quite fine. In fact, this number changed. It was much, much higher than that. It was in the 90s. Either way, this code is very nice, very elegant. You can even shorten it. You can just do something like this, make it look nicer. And there you go. It's just a couple of lines, really. 1, 2, 3, 4, 5 lines of code solving a potentially interview question. We're going to be solving a question called the 3-sum closest. And the question says, given an array nums of n integers and an integer target, find the 3 integers in nums such that the sum is closest to the target. Now return the sum of the 3 integers. You may assume that each input would have exactly one solution. So let's really understand what that means through an example. We have an array here called nums, has -1, 2, 1, and -4, and a target of 1. We want a triplet, so 3 numbers here randomly, that which their sum is the closest to 1. And just by looking, we can see that if we add -1 plus 2 plus 1, we get 2. And this is the closest thing to 1. Because let's pretend we're going to add, for example, a different triplet, -4 and 1 and 2. It's going to be not close, right? It's not going to be the same thing. It's going to be 2 numbers away. So that's the whole point, is that you look for a triplet, and that triplet's sum is the closest to that target. Now that we understand what the question is asking of us, let's solve this question. Oh, by the way, the constraints is just don't do anything crazy, that's all. Now, let's solve this question. First, let's give you a visual representation of it. Let's start here with explaining how this mathematically works out. So it's basically the first number plus the second number plus the third number, right, is supposed to be approximately equal, well, not approximately equal, just approaching a target value, okay? But since we can't get this target value exactly, so it's not exactly equal, what we can do instead is simply change this equation a bit and make it into an inequality. And we can say that target is equal to all the numbers. Remember, the numbers are, the sum of the numbers are number 1 plus number 2 plus number 3. Okay? All of that sum here. Let's just put it here. See what happened here? We got the sum of the triplet and we subtracted it from the target. Now we cannot here make it equal to 0. So what we can do instead is think about 2 different cases. If it is larger than 0, if it is smaller than 0. Well, if the target is bigger than the sum, then we need the sum to get bigger so we can approach it. So in that case, we need some methodology to make the sum bigger. And likewise, if the target is smaller, then the result is going to be a negative value, which means that we need to make the sum smaller, and we're going to need some sort of methodology to do this. Luckily, the two-pointer method is going to come to the rescue. And we're going to use this two-pointer method to have a pointer at the beginning of the array and a pointer at the end of the array. Now, if we move that pointer, that last pointer, backwards, the sum is going to decrease. If we remove that first pointer forward, the sum is going to increase. And that's the methodology that we're going to be using. And in order for that to work, this array needs to be sorted. And luckily, we don't need to keep track of any indices, so there will not be any issue when it comes to sorting. And that's really how we solve this question. If you don't understand through this visual representation, it's completely fine. Some people understand better through code, and hopefully you're one of them. So let's get started. Okay, so first we're going to need a variable to store the closest difference. Okay, and I'm going to make it into something like infinity, okay, something insane. And then we're going to simply sort the array. Just so you know, just like that, it's an n log n complexity. Okay, because in Python it uses timsort. Anyway, so for I in range len nums. Now what are we really doing here? We're simply getting the first number. Okay? So the first number, number 1, is going to be equal to nums I. Here's the thing, right? We may have multiple triplets, and we may have duplicate numbers. So in order to avoid this, I like to do this neat little trick here. If I is larger than 0 and nums I equal to nums I minus 1. The reason I put this I is larger than 0 is because I don't want it to compare to something outside the bounds of the array, right? And we're simply going to continue. So if we have any duplicates, just simply continue and don't do this again. Now we're going to simply use the two-pointer method. We're going to use the two-pointer method in our programs. The left pointer is going to be the I plus 1. So it's going to be one step further after this, the index of the first number. And the right pointer is going to be at the end of the array, nums. And we're going to loop until the right pointer is no longer larger than the left pointer. Okay? So now we can get the current sum. The current sum is simply going to be equal to n1, number 1, plus nums left plus nums right. This is what we were talking about. This is what we're going to subtract the target, use to subtract from the target. Okay? Now, if the target subtracted by the current sum is equal to 0, then this is just the optimum value because it's exactly equal, right? So we're just going to return the current sum and be done with it. That's it. Call it a day. However, it's not always that straightforward. So we're going to do something for if it is larger and if it is smaller. But before that, let's just store the closest difference. So if the current difference, let's make a variable for that, current difference, equal to target minus the current sum. So if the current difference is smaller than the closest difference. Now, let's think about this for a moment. We cannot compare this to this because this could be worth a negative value, and this could be worth a positive value. So in the instance where the current difference is equal to 5, for example, and the closest difference is equal to negative 5, it's not a very fair comparison, right? Because sometimes things are different. So what we need to do is to just apply an absolute function on it. Now, once we have that, we can simply update the closest if that is in fact the case with the current difference. Now, why do we need to do that? We need to do that so we can eventually subtract that from the target, and then we can get the current sum. You'll understand as we go. It's a bit confusing, I know, but with enough perseverance, you're going to get it. So if the current underscore difference is larger than 0, what do you think we should do? Well, if the current difference is larger than 0, then maybe I should make the current sum larger, right? So left plus 1. Why? Because this was the methodology. This was the methodology for getting the values to be bigger. However, if it's anything else, and by anything else I just simply mean if it is smaller than 0, right, minus equal to 1. Once that is done, we are simply going to return closest underscore difference. Now let's check and see what we have here. We are returning closest underscore difference y. That doesn't make sense, right? It doesn't make sense to return the closest difference, because what we need to return is the current sum, right? What does the closest difference really entail? Well, it's target minus current sum. So if we remove the target, then we simply get the current sum, right? So let's do this. So target minus closest difference. Work this out on a piece of paper, and you should be able to get it right away, no problem. Oh. There we go. And here we go. I'm going to be answering the question, the longest substring without repeating characters. So the question goes as follows. Given a string, S, find the length of the longest substring without repeating characters. And substring is different from subsequence because substring implies that it's contiguous after each other, but subsequence implies that it's in the same order from left to right. Okay, so let's look at the examples. Example number 1, it says the string is equal to ABC, AB, CBB. Okay, and the output is equal to 3. Well, the reason for that is because we have 3 distinct characters after each other, ABC, but once you hit that 4th character, it becomes repeated. So you have the A at index 0 equal to the A at index 4, and that's a no-go. So we only stop at ABC, which has the length of 3. Okay, now let's look at example 2. Example 2 is a string filled with only 1 character. So naturally, the output for that would be 1, because B is the only distinct character we have here. Now look at example 3. Example 3, we have WKE in the middle as 3 distinct characters. Anything before that would have 2 W's, which is a duplicate. Anything after that would have also 2 W's, which is also a duplicate. So that wouldn't work out. And here they explain what we just talked about. Notice that the answer must be a substring. PWKE is a subsequence and not a substring. This is what we talked about. Finally, example 4 is an edge case. Well, if we don't have any strings in our input in the first place, what do? Well, we simply put a 0. So let's get into our editor. So let's have a look here. Okay. First, we notice that it's a substring. And second, we notice that it's contiguous. So one idea that might work is the sliding window technique. In order to have a sliding window technique, we must have a window start and a window end. For those of you who don't know what this technique is, it's just simply something like this. If we have an array, 1, 5, 3, 6, 7, 9. Let's say we want to calculate a specific substring. So what we do is we move the ends of the array and the beginning of the array towards that area of interest. So something like this. We'll move till we have a specific substring. So out of all the array, the answer that we want, for example, is going to be 6 and 8. And this is exactly what we're going to do here. We're going to look at this entire string, and we're going to move and position the end and the start of the string in the area of interest. And once we do that, we take a snapshot of that point in time and get the required information, which is the output. And the output here is 3, and then we continue with our algorithm. If that snapshot in time is still what we want, is still what we desire, then we keep it. If not, then we change things about. And that's the sliding window technique in like 3 minutes. So let's move on to the specific of this specific problem. First thing we'll do, we're going to start with the window start, which is going to be equal to 0. And we're going to put in the longest, a variable called longest that describes the output. So the longest is the output here, and the window start is basically the beginning of the array. Now, let's move on to the character index map. The character index map is simply a hash map that we're going to use to be able to jump around in our array. So for example, if we have A, B, C, A, as soon as we hit A, we have a repeated value, which is the A. So we no longer want to consider that first A. So we need to find the location of A and then go a step beyond A, just a single step beyond A. And that's what we need to do. And that's why we need a hash map. That hash map, or that dictionary, would store every character along with its index, so we can access it at our convenience. And when we can access it, we can go a step beyond it. And when we can go a step beyond it, we can make the window smaller from the left side. And when we can make the window smaller from the left side, we can close it down and narrow it down to the part where we want to get the sequence or the substring of interest. Okay, so let's loop through the string. So window end. I did notice that I didn't name it I here. I named it window end because that is going to represent the other side, the window end, the right side. So when in range, the length of S. We're going to get the current character. So current char is going to be simply S, the current string, accessed at the end of the window. Notice that at the beginning of the loop, the window end is equal to 0 and the window start is equal to 0. So they both start here. And the array goes on like that. Okay? So they both start here at 1. Okay? And then it expands and shrinks to meet our desired requirements. Okay, let's move on. If that current character is in the hash map, then it is a duplicate. Okay? If it is not, then we could just simply move on. But what happens if it isn't a duplicate? Well, if it is a duplicate, then what we do is we adjust the window start. We make it shrink a bit. Okay? So window start is going to be equal to that exact index plus 1 step further. Okay? Now, once we've done that and we no longer consider A, we have to update the index of the current A. So what we can do here is simply just copy this and make it equal to the window end, just for the sake of it being updated constantly. Now that we have basically the meat of the code done, we need to calculate the output. We need to calculate the window size. And the way to do that is through this. Window size is equal to the window end, the end of the window, minus the window start plus 1. Now, notice that I added 1 here, and the reason for that is because this is not the subtraction of an index. We are trying to calculate the length. Okay, so we're subtracting the index, but not only that, we're adding 1 to get the length. Finally, we are looking towards the longest output substring. So whatever it is that we had before, we're going to get the max between that and the current window size. Once our for loop is over, once our program is over and it stops running, then all what we have to do is simply return the longest. Now that this is done, we can run our code. Right, now let's submit it. Right, so there is an error here. Have you noticed why this error exists? Well, actually, it's quite simple. It's because there is a situation where the window start is actually ahead of the char index map. You understand? So if the window start is ahead, why would I ever go back? Why would I ever jump backwards? I always want to jump forward and not backwards. So I hope that you learn from this specific edge case, because this is the part that I want you to think about on your own. And there you go. There's the answer. Everything works quite fine, runs perfectly, and that's it. Going to be solving a question 3 sum. Now let's read that question. Given an integer array, nums, return all triplets, num_i, num_j, and num_k, such that I doesn't equal to j, and I doesn't equal to k, and j doesn't equal to k. So if you don't understand so far, I, j, k are basically indices. And nums_i plus nums_j plus nums_k is equal to 0. So we want 3 numbers in an array that add up to 0. That's basically what the question is. It's just very poorly worded. So notice the solution set must not contain duplicate triplets. So here is example 1. We have nums -1, 0, 1, 2, -1, and -4. So just by looking, you can see that -1 and -1 plus 2 is equal to 0, and same for -1, 0, and 1. If you have an edge case where you don't have any input, just return nothing. Just return an empty array. If you have an input that has only 1 value, then simply return nothing. It's the same thing. And the constraints are basically telling you, hey, just don't be crazy, okay? That's all. The related topics are array, 2 pointers, and sorting. So let's think about this question without having that hint that we just got, the 2-pointer and the sorting. Well, really, if we're looking at 3 values, then the naive way to do it would probably be something like a 3-for loop, which would result into something like an n-cube worst case scenario for your big O, which is terrible. This is not something that you would want for an interview question. And in fact, it could lead to time limit exceeded if you're solving it on an online judge, if it's an online assessment or something, right? So instead, what we can do is lower down this, this complexity using something like sorting. So what does sorting do for us, really? Well, what sorting does for us, it allows us to use techniques that are only feasible if that array is sorted, like the 2-pointer method. The 2-pointer method, if you're not familiar, is basically that you have two different pointers pointing at two different ends of the same array. So let's look at this array, for example. We have 1, and then 5, and then 3, and 4, and 10. If we look at this array right here, and we want to find, for example, two numbers that add up to, let's say, 4. So if we are using two-pointer method, then what we'll do is we'll have a pointer here and a pointer here. And we'll compare that to our target number. So our target number is, for example, 4, right? So we'll look at 1 plus 10. Well, it turns out that 1 plus 10 is too large. So what we'll do is that we'll move that pointer back a bit such that we can compare it again. 1 plus 5 is larger than 4, which is not very good. We can move that pointer again. 1 plus 3, well, 1 plus 3 is in fact the value that we want, and we can simply return that. On the other hand, if the value that we were looking for was something like 5, for instance, so let's say it changed the target value here to 5, then what we'll do is we'll move this back a bit, but as soon as we hit this point right here, we're going to have to move the other pointer forward. And that's the two-pointer method for you in less than, 3 minutes. But this technique could solve the 2-sum problem, but not the 3-sum problem, not when you have a triplet. So how can we mitigate this? Well, simple. What we can do is we can think about it in terms of x plus y plus z. Let me show you. We're going to use the same logic, just so you know, but it's just bigger. So x plus y plus z is supposed to be, in this question, equal to 0, which means that x could move to the other side by being negative x, which means that we can turn this question into a 2-sum question, but the target sum in this case is the negative x and not the 0. And that's how we solve this question. So let's start with our problem. First, let's create an array called triplets. This array is going to be a list of lists, an array of arrays. Okay? And we're going to loop through every number inside the nums. Why? Because we're looking for our x, you see? So nums. And let's give ourselves some room. Okay. So we need to get the current value. Well, let's name it the target sum. Okay, let's give it more meaningful names. Nums I. This is going to be our target sum. But there is an edge case that we need to treat right away. What if we have more than one value with the same value? So for example, like a bunch of 2's after each other. Because remember, when you sort the array, all the numbers that have the same value will be directly after each other. So that's something you need to account for. So if I is larger than 0, and you'll see shortly why I is larger than 0, and nums I is equal to nums I minus 1. That's why I is larger than 0, because, you know, if you have 0 minus 1, that just doesn't make sense. So if that's the case, then we are simply going to continue. We're just going to ignore this duplicate and move on with our lives. Okay? For every number, for every negative x, or in this case just simply x, it's not negative yet, we are going to search for its y and z. So we're going to search for its y and z. So we're going to search the target sum. So we're going to create this function right here that does this search, that does the logic that we explained earlier for the two-pointer sum. And once that is over, we're simply going to return the triplets array with the answer. So let's move outside this function now and write this search method. So def search, and we're going to pass in the array. It's called nums here. I'm going to pass the target sum. And we're going to pass the left pointer only and not the right pointer, because the right pointer always starts from the end. But in this case, we want the left pointer to start after our current x index. So it's going to be I plus 1. Follow along here if you don't understand, and it should be clear to you. Okay. And of course, we're going to pass in the triplets array because that's really what we want to return. That's the whole objective of this question. So now, the right, wait, let me name this left first, because I plus 1 is going to be what happens after we pass the value. So right is going to be equal to len of nums minus 1. Okay, brilliant. Now that we have the right pointer pointing at the end of the array, and the left we're basically waiting on it. In fact, let's do this right now. So the search would take the nums array, the search method I mean, and the target sum, and would also take I plus 1 as the argument for left. And the reason for that is because we start one step after the current index of x. Okay, I hope that's clear. And the triplets is going to be the actual return. That's what we want to return. That's the whole point. Now, let's go into the meat of the code. Let's move in a bit, leave ourselves some room. Let's get up. Now, let's think about this. We want to search until when? Well, until the left is no longer larger than the right, because that means that we've searched the whole, section. Okay? So while left is smaller than right, keep going. The current sum is going to be equal to nums left plus nums right. Okay? If that current sum is equal to the target sum, then do something, right? Which is triplets dot append. We're not returning here, remember, because we want to get all the instances. Dot append the nums left, the right, and the target sum. So the target sum, and let's zoom out a bit, and the target. So the target sum and the nums left and nums right. Okay? Now, hold on a second. We're not really comparing the current sum with the target sum, are we? We're comparing what to what again? We're comparing the current sum with the negative of the target sum. So we should change this into negative current sum. Now, once that's done, then this area has been searched and we could just simply move on. So left pointer could be pushed by 1 forward, and the right pointer will be decreased or decremented by 1 backwards. Okay, but there was something that we found to be interesting in our answer, which is that notice the solution set has no duplicate. So we have to check whether or not the solution was there before. So one thing we could do is simply say, hey, you see all that? Just make sure that that's not in our triplets, not in our triplets. So you could do that, right, using a simple if statement, and this would be correct, right? However, at the end of the question, I will show you a better way to do this because this is a little bit expensive than what you might think. Anyway, back to the meat of the code. So L if the current sum is larger than the negative of the target sum, then what do we do? Well, if the current sum is larger, then what we have to do is simply reduce that value. So right is going to negative equal 1. Okay. What if it's the other way around? What if the current sum, let's make it LF so it can be as explicit as possible. Current sum smaller than the negative target sum. Well, that means we need to make the current sum bigger. So left plus equal to 1. Okay, now that we have the meat of the code basically there, then what we need to do is think about two things. The first thing is, what are we returning? Well, we're not really returning anything here, right? And the reason for that is because triplets are passed by reference and not by value. So everything's good. And besides, if we decide to return anything here, everything will be done kind of preemptively, and it would have been a bit weird to return this. I mean, it would just be weird to return something here because we're not storing anything, right? We're just returning it at the bottom. Now, the second thing we need to think about is the duplicates thing that we talked about earlier. And it's one thing to avoid the duplicates here, and another to avoid the duplicates of the triplets down here. So instead of checking if, for example, if the whole target sum and the left and the right is in the triplets, and if so we can continue, I'll do something a bit different. And I think that's faster and less computationally expensive. So while the left is smaller than the right and the nums left is equal to nums left minus 1. So if the nums left and the nums left, the index before it is equal to each other, then what we'll do is just simply move on with our lives. The same thing can be applied to the right pointer. And nums right equal to nums right, not minus 1 in this case, probably be plus 1, because we're moving backwards with the right pointer. So right minus equal to 1. Now, this is our code. It's effectively done. This is as optimal as I can get it to be. If you find this a bit confusing, you can just simply do the thing that I told you about here, right? Yeah, that's it. Let's see. Let's hope this code runs right away. No errors. Hey, there we go. It runs successfully. Now, you're going to be solving a question called the force sum. Now, this is the medium level of difficulty question on Leetcode. And the idea here is that you need to find 4 different values in an array that make up a singular value, right? Let's read the question. Given an array nums of n integers, return an array of all unique quadruplets, and unique here is in bold. Nums A, nums B, nums C, and nums D, such that all those indices are between 0 and n. Now, A, B, C, and D are distinct, so they have to be different. And they have to make up the target value. So the input is going to be an array and a target value. So there we go. We have nums here and 0. Just by looking, you can see 3 quadruplets that add up to 0. -1, 0, 0, and 1 is indeed 0, and so are the others. And here's another example underneath, but this time it's basically only 1 entry. Now notice how there is duplicate values here, right? Like this is 1, 2, 3, 4, 5. These are 5 different 2s. But then again, the output is only a singular array. Now the constraints are basically telling you not to be crazy. But other than that, we have nothing else to go on. So in order to solve this question, I think a better way to solve this question would probably be to think about what we would do with a 3-sum question, okay? And then think about how we would solve that question in a 2-sum question. So let's go down to the level of 2-sum. So let's change this question a bit into making it a 2-sum question, okay? Here's our array. And in this array, we want to look for 2 numbers that add up to the number 7. So our target here is 7, and our array nums is equal to that. Now, one way we could do this is basically have 2 for loops going over it and brute forcing the heck out of it until we find the actual values. But this runs in n squared. We can, however, solve this in a different way, right? we can sort this array into this. And then we could use the information of it being sorted to help us use the two-pointer method. And the two-pointer method is as follows. You have a pointer on the left side of the array and a pointer on the right side of the array, usually at the end of the array, right? And we loop through this array according to the target, how far we are from the target value. So, for example, let's say we start here at 1, which is the left side, plus 10, which is equal to 11. Is 11 larger than 7? Yes, it is. So what we can do is make that number a bit smaller. In order to do so, given the fact that it is a sorted array, we can simply move the pointer a little bit backwards. Which pointer that is? The right pointer. So here, and we get two new numbers, 1 plus 7. Is 1 plus 7 larger than 7? Yes, of course it is. So we can once again make the number smaller. Right. So now we have 1 plus 6. Is 1 plus 6 equal to 7? Yes, it is. So we can store these two numbers, 1 and 6, in our array. Okay. Since we got both of them successfully, we can move both arrays, both pointers forward. This and that. Okay. And we're going to compare once again. Is 2 and 5 the same size, the same value as 7? Yes, it is. So we're going to add here 2 and 5. And we're going to move both of these pointers forward. Now notice how they switched positions? That means we're done with the actual search, because we're going to just be going in circles, which doesn't make much sense. So we're going to stop at where left is larger than right, right? So in other words, while left is smaller than right. Okay? That's the whole idea of the two-pointer method and getting the two sums. Now, in order to solve our question, what we're going to do is use that exact same logic, just within two for loops. And then we're going to use our logic. That's the whole thing. That's the whole idea. Nothing really too different from what you used to be solving, to solve before. So let's start by solving the question. So for this, we're going to first sort the array, like so, and then have a variable to store in all the quadruplets. We're going to call it quad. For I in range len nums. And just a small little bit of optimization there. I'm just going to make it -3 because this for loop is going to be in charge of the first value. Now, we want to avoid any duplicates, so we can avoid their entire run through. So we can say that if the I is larger than 0 and nums I equal to nums I minus 1. The larger than 0 makes sense now, right? With this value, nums I minus 1, because you don't want to go out of bounds. Now continue, if that is the case, because you want to skip it completely. Okay, if we do find that it's not a duplicate, then what we can do here is for j in range len nums. Also a nice neat trick for optimization here is -2, because this is in charge of the second number, right? Anyway, if j is larger than I plus 1, because we still want to compare backwards, and nums j equal to nums j minus 1. Different values, same story. Continue. Now, we have our two for loops. Now let's implement the two-sum logic that we just implemented. Okay, here we go. So for this, I'm going to create a function for that because I don't want to get confused on how to do this, right? So I'm just going to write search. And this will have our two-pointer method logic. Okay, let's implement this function. Oh, that's as far back as we can go. Search. Okay, what do you think the parameters for that would be? Well, first, there is the nums, the actual array. And then we have our left, and we have our right pointer, and we have our target sum, right? And we also have our quad, because the quad is actually what we're going to return. Eventually, that's the output, right? But since we know that the right is always at the end, so probably no need for that. We can just initialize that inside of the function. But the left varies, right, every time, so maybe keep that in. And if there was any more parameters, we're just going to figure it out as we go. Now let's copy this exact same thing and put it here. Okay. Now let's start. The right is always equal to the length of the array. Here it's called nums minus 1. And the left is going to start one step further after the last number, right? After the last index. So simply, and the last number is j. Oh, pardon me. And the last number is j. So j plus 1. Great. Now, we still didn't answer the question of what is the target sum. We do have our target, but what is the target sum? Okay, so the target is supposed to be equal to the first number, nums I, plus nums j, plus nums left, plus nums right. If we do have both of these numbers, but we don't have these numbers, then what we can do is simply shift that to the other side, like so that we can simply focus on these two numbers, right? That's exactly what we'll do. And the value coming from that is going to be our target sum. So this is going to be target sum, called target sum, and this is going to be a target sum, okay? Anyway, so here, let's initialize our target sum, which is equal to the target minus the known, which is known nums I, plus nums, you guessed it, j. Now, while left is smaller than right, then let's start. First, let's get our current sum. Our current sum of the two pointers is going to be nums left plus nums right. Okay? Okay. If our current sum is equal to the target sum, then here we've successfully found a quadruplet. So what we need to do here is simply add it and not return. We need to add it to the list, which is going to be a list of lists. So nums I and nums j and nums left and nums right. I know it's annoying, but you know, it is what it is. Anyway, elif, what if the current sum is actually smaller than the target sum? What do you think we'll do here? Well, we can move the left point forward. But hold on a minute. After we find these duplicates, we don't want the left pointer to be and the right pointer to be stuck where they were, right? Like in the conceptual visualization that we saw, we need to move both pointers forward, right? If it is smaller, it's gonna we're gonna try to get it to be bigger by pushing this forward. And if it is larger, so elif current sum is larger than the target sum, right? I'm just writing it out for you, but really what we need to do is just simply write else. Then right minus equal 1. We're going to move that pointer backwards. So here it's forward and here it's backwards. And here we're just simply moving the 2 pointers in the opposite direction because we found a duplicate. Now, up until now, the main logic is done. The main meat of the idea is done, right? Now, what we need to cater for is that unique, okay? We want to make the values unique, which means that as soon as we find a duplicate, we have to make sure that it is no longer in question. So while left, by the way, the duplicate could come from either sides, from the left pointer or the right pointer. So while left and nums left is equal to nums left minus 1, then what we need to do is just simply move the left pointer forward because it's futile to stay where we are. We can do the same thing for the right pointer. And nums right equal nums right. What do you think it will be? Minus 1 or plus 1? Well, it's going to be plus 1, and the reason for that is because we're coming from the end backwards. And the thing before that is at the end and not before it. So right minus equal 1. That way, we avoid any duplicates for the 2 pointers here. And that way, we avoid any duplicates for the first 2 numbers. This way, we can avoid duplicates in general. Now, once we're done with all of this, we are simply going to return the quad. And the reason why we can return right away here is because this is by reference and not by copy. Okay? Now we're going to run this. Let's hope we don't run into any issues. I think I messed up something, but let's see how it works out. Okay, I is not defined. Let's see. Oh yeah, we didn't pass I here. I and J, we didn't pass them. Right? And we didn't start here I plus 1. Okay? Now let's submit. And it works perfectly fine. So let's try submitting this time. Brilliant. So the answer is actually faster than 99%, 0.83 of all Python answers, which is a great success. Hey everybody, how's it going? In this video I'm going to be solving a question called backspace string compare. Now this is a Leetcode question of easy level of difficulty. And it goes as follows. Given 2 strings, S and T, return true if they are equal when both are typed into empty text editors. And the hash sign means a backspace character. Note that after each backspacing an empty text, the text will continue to be empty. Okay, that's a bit cryptic. Now the example goes as follows. We have 2 strings, S and T, and they are AB backspace C, AD backspace C. So if you backspace starting from the hash here, you backspace the D, it removes it, that means we're left with only A and C. Same thing goes here. If you backspace here, you're left with only A and C, which means they're both the exact same thing. That means it is true. So it turns out that this question is actually asking you if these 2 strings are exactly the same post backspacing. That's really what the question is asking of you. And I know it's a bit cryptic here, but that's really what it's asking of you. And example 2 is more or less the same, only this time you have 2 backspaces. So one backspace is the D, it removes it, and one backspace is the C here, and then we're left with really nothing. Same thing goes here. You backspace twice, and you're left with nothing. Here it's a bit different. Because after you're left with nothing in both sides, this is considered the same string, right? So the output is true. Now let's move on to example 3. Example 3 Look here, you see that hash symbol? You backspace before writing the A. So there's nothing to backspace over here, okay? So once you move on to the next backspace, you backspace the A, then you're only left with C. Now, if you do the left side the same way, in the same fashion, you'll figure out that these two backspaces, one of them is going to remove the A, and the other one is just basically going to remove nothing, so you're only left with C, which means that both strings are the exact same thing. The output should be true. Pretty straightforward idea. It was just really hard to get there. Now, let's solve this question on the whiteboard. Oh, the blackboard, I mean. So let's think about how we would solve this question without the backspace. Well, the idea here is that we're going to scan both strings at the same time, the one on the right and the one on the left. And we're going to move from start to end, comparing every character. If none of them, if the first one is equal to the first one in the other array, and then the second one is equal to the second one in the other array, and the third one is equal to the third one in the other array, and so on until the end, that means that they are identical. But if somehow in the middle, one of them is not equal to the other, then that means they're not equal. That's how we would normally solve it, right? And we can do the exact same thing in reverse, right? We can check from front to back. But this is how we would solve the question without the backspace. So we need to mitigate this situation. And in order to do this, we need to check for the next valid comparison. Because here the hash symbols are neatly placed after each other, right? So you can make an argument that, hey, maybe I could skip one step behind that. And you might be right, but that wouldn't always work. So what you want to do is figure out the next valid index. The left pointer and the right pointer are indices in their own right, just so you know. They're just simply pointers for visual representation. Now, let's look at how we would do this in code. So here we have our editor. Let's start. First, let's have our left pointer, len s -1. It starts at the end of the array. We're going to make that pointer scan from the end of both arrays. And we have the other pointer, len t. We're going to make that scan from the end of the array. Let's give ourselves some room here. And since we're scanning both arrays simultaneously, then we have to make a condition for both of them. So while left is larger than or equal to 0, which is the beginning of the array, or right is larger than or equal to 0. And the reason why we did this here is because we're scanning simultaneously, so it's or, not and, because one of them could potentially be longer than the other. And if that is the case, then that means we do not have the same string. Okay, let's move on. Now, we need to get the next valid index. So the next valid index for the left pointer is going to be left equal get next valid index. Okay, this is a function to get the next valid index. We're going to define this very shortly, but I'm just walking you through the logic. Now, right valid, this is going to get the next valid index as well, right? And we're going to have in it our array, right, and our pointer. Our array and our pointer, right, for each side. Now, if the left index is smaller than 0 and the right index is smaller than 0, then that means both of them have reached the end, or rather the beginning of the array, because we're scanning backwards, which means that we've run through no problems, right? Because remember, if we find something that isn't the same, then we would say, hey, that's false. So return true. If on the other hand, one of them reaches the end before the other, So right underscore valid smaller than 0. Then return false. And now for the real comparison, which is if s left valid, if the value at the current index of the left valid pointer does not equal to t at right underscore valid, then also return false. So we have here 3 filters to see whether or not you have the right condition or not. And the reason why there isn't any elif here is because return false just simply ends the function. So it's all good there. Now, let's define this long-awaited get next valid function. Okay, but before that, let's just end the function nice and neat. Return true if everything else was not matched. Okay, so this function, like we said, is going to take a string, right? Whether it's the s or the t, and it's going to take a pointer, right? Whether it's the left pointer or the right pointer. Let's think about how we could get the next valid. So for starters, we know that it's going to go backwards. So index, whatever index, let's name this index instead of pointer, okay? Because that's easier for us conceptually. So the index is going to keep going backwards. So index minus equal to 1, right? Okay. But this is at the end of everything. What we need to do before that is to deal with the backspace. So the backspace starts out as 0 because we don't know if we have backspaces. But as we go, so while the index is larger than 0, right? While the index is larger than 0. If the string value at this current index is equal to the hash symbol, that means we have a backspace. Okay? If not, elif, if not, we don't have a backspace, that means that the backspace could potentially be something else, right? It could be 0, it could be lower. So in the case or the event where it's larger, then what we need to do is set the backspace back to -1. Otherwise, where the backspace is equal to 0, then we need to break. Finally, we have the index inside the loop minus equal to 1. Now, this is the whole point, right? This whole mechanism right here is to delay it until the backspace is being handled. If the backspace is not being handled, we wouldn't have gotten the valid space. So that's really how it works, right? Finally, when we're done with everything, what we need to do is to return the index. That way we can get the values, right? So, but we notice something very interesting here, right? Is that we do go a step backwards here, right? But once this loop is over, we also need to go a step backwards. So left is equal to whatever the left valid value is -1, just to keep the loop rolling. And the right is the same thing, and it's going to be right and then valid -1. Now let's see what we're missing. Are we missing anything? Is there any edge case we didn't consider? Okay, so there isn't a case that we did not consider. Right, so the case we didn't consider was if the index is exactly 0. So let's try submitting this time. Brilliant. So the answer is actually faster than 99%, 0.83 of all Python answers, which is a great success. You know how the myth goes, right? You're not a real engineer, you're not a real software engineer unless you can invert a binary tree. So let's get started with this classical question and read it so we can fully understand it before we actually tackle it. So given the root of a binary tree, invert the tree and return its root. Okay, so what does it mean to invert a tree? Well, it doesn't mean that you have the root as the leaf node and the leaf node as the root. No, that's not what happens. What it means really is that everything on the left side of the subtree becomes the right side of the subtree and vice versa. And that's really how it goes. Look at this visual representation for a moment and you'll quickly understand what I mean, even without going into details. So if you look at the array representation of this tree, you'll find that the order of it changes to represent this exact structure. Now, example 2 is the same thing, what you might expect. If it's 1, 3, it becomes 3, 1. So let's solve this question really quickly. Okay, so we are going to solve this question recursively. And we are going to swap the roots, right? So really what we're going to do here is root of the left subtree is going to be equal to the root of the right subtree, right? And the root of the right subtree is going to be equal to the root of the left subtree. Okay, great. Now, we're going to keep doing this until the node is none, right? Until it's the end or the bottom of the tree. So if root is none, let me just, there we go, return. Okay, now let's keep doing this. And how do we keep doing this? We're going to do this recursively. So just copy this, right? Self, and let's just go right ahead. Now here's the thing, right? We can't say root, right? Because we don't just want it to be applied on the root. We want it to be applied on the left subtree and the right subtree. So dot left. And then we copy this exact same line here. Do it again. Just this time for the right subtree. Simple, right? So what's going to happen here is that it's going to run through the code. If the root is none, it's going to return none. If it's not, it's going to swap whatever that node is with its counterpart. Now, once that's done, we're going to run this program recursively on the left side of the tree. And it's going to restart, go back again, and do these exact same steps. Once it reaches the end of that node, it will break out of this loop, and it would start working on the next line, which is the one for the root dot left. After everything is done, we want to return the very, very beginning of that tree, which is originally the root. So we're simply just going to write return root. Now, if you don't understand what I'm saying, then maybe you don't understand recursion properly. And if you want a video about this, please let me know. All right, let's see here what's going on. Oh. Okay, and it runs perfectly fine.
Don't say it. Don't you say it. Left. Come on!
Everybody, how's it going? In this video, we're going to do something exciting. We're going to solve our very first linked list question on this channel. And this question is going to be linked list cycle. Okay, so let's see how this works. Given a variable head, the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in the linked list if there is some node in the list that can be reached again by continuously following the next pointer. Now, internally, POS is used to denote the index of the nodes. That tails the next pointer is connected to the node. That POS is not passed as a parameter. Now, return true if there is a cycle in the linked list, otherwise return false. Now, we can clearly see that the output of this function is going to be a Boolean value, so nothing to calculate, just simply to verify. Now, here we have a linked list in example 1, 3, 2, 0, and -4. And by the end of that node, it turns out that we go back in a cycle fashion to a node in the middle, which is 2. So that means there is a cycle. Now let's solve this question, right? Let's open our Blackboard here. So the way we're going to solve this question is using something called the hare and the tortoise method. The hare, here's a hare. Let's pretend that's a hare. And the tortoise. Okay, you love my my exciting drawing? So the idea of the hare and the tortoise is basically there is one that walks very slowly and one that runs extremely fast. Do you remember that scene in Avengers where we have Anthony Mackie running and then Steve Rogers just runs and he keeps saying on your left? See, he runs in cycles. Both of them are running in circles, right? But every once in a while, Steve Rogers catches up to Anthony Mackie. Now, let's see how this would work out here. We have the hare, which is denoted by the blue pointer, and we have the tortoise, that is denoted by the rainbow. Now, the hare, because it's fast, Steve Rogers, the blue one, is going to take 2 steps at a time. So it's going to be 1 and then 2. But Anthony Mackie, on the other hand, is going to take only 1 step. Now, again, Anthony is going to take 1 step, while Captain America, the hare, is going to take 2 steps. So that's step. And then, since this is a cycle, it's going to go all the way back. That is another step. And we go forward again. 1 step. And then Captain America is going to catch up to him and he's going to be like, on your left. Now, this on your left thing that we have here, this is basically showing that this is a cycle. Because no way would this have been possible if they didn't run around in circles. And the reason why we have it as 1 step and 2 steps is because if you do any more than that, there is no guarantee that it will actually converge in the manner in which we aspire it to be. So this is a more or less convenient way we can solve this question. And it's very fast. I solved it before I opened this video, and it got me like 99%, Python speed. Anyway, so let's solve it in code. So we have Anthony Mackie, right? Mackie, and Steve Rogers, Captain America. Cap. And they're both starting out at head, right? Now, while Cap is cap.next is not none, right? And cap is not none, which means that the current cap is not none, and the upcoming step is not none as well. We need to do that and check right ahead of time. Okay. Now, Mackie is going to take 1 step. So dot next. Cap, because he's faster, he's going to take 2 steps. Okay. If Cap catches up to Mackie, then he's going to tell him, on your left. And really, if that doesn't happen, then this all has been for nothing. And this is not a cycle. Okay? So yeah, that is basically how it works. Let's run this. Now, let's submit this. And there we go. It says 44, but I could have sworn it was 99. Let me try this again. Let me see. You see, 93.59. So yeah, that's the question for you. It's pretty nice, pretty neat. So we'll be solving the second linked list question on this channel. So linked list cycle 2 is the question at hand. It's a medium level of difficulty. Given a linked list, return the node where the cycle begins. If there is no cycle, return null. Now it's important to know what this cycle begins is. What's the definition of that? We need to think about that later. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, POS is used to denote the index of the node that tails the next pointer. Now it's very important that you understand this bit right here. Pointer is connected to note that POS is not passed as a parameter. Notice you should not modify the linked list. Now, I understand better through example. So let's look at this example. Just by looking here, you can see that there is a cycle, right? And it's between -4 and 2. However, due to the definition that we read earlier, the tail is next pointer, the cycle doesn't start from the node that has the value -4. It only starts from the node that has the value 2. That is the beginning, not the -4. Funny enough, while the output is simply talking about index 1 and all of that, we don't really need to return any index here. The only thing we need to return here is the actual node where the cycle starts from. So you see the problem here is that this question is simple but very cryptic. That's the problem with this question. So anyway, what we need to do is simply return the node at where the cycle begins. Now, let's solve this problem in the blackboard first before we start coding. Now, before we do anything, we need to check if there is a cycle first. Because if there isn't a cycle, then it would be futile just to even attempt this, right? We just return none. However, if there is a cycle, then maybe there's some talking we should do. That's the first thing. And we do this through the hare and the tortoise method, where we have 2 pointers, like so, one fast and one slow. The fast one takes 2 steps, 1, 2. And the slow one takes only a single step, so 1. And then 1, and since this is a cyclic, we take another 2. And this, of course, takes the 1. Right? Anyway, so we keep doing this. This takes 1, and this takes 2 until they meet at a certain point. If they do meet, that means that this linked list has a cycle, which means that we can move on and continue with this logic. Okay, now the next thing we need to do is really calculate the length of that cycle. So by cycle, I mean the area 204, right? 20-4. So just by looking, this is clearly 3, right? Now, why do we need to do this? Because if we can put one of these pointers away by the length of that cycle, we can figure out where the position is. Let me show you. So the length is 3, right? So 1, 2, 3. Okay? We have our starting point. If we move both of them just a single step forward, guess what happens? So let's move this first, and then let's move this. They intersect again. But only this time, they intersect at a meaningful place, not just a random place to check it for a cycle. No, it checks at the beginning of that cycle. And this is where everything matters, right? So that's why we need to do those steps in the following order. Check for a cycle so we don't waste our time, and then check the length so we can put one of the pointers ahead. That way they can move eventually and meet at the beginning of the cycle. And that's the whole logic behind it, right? Now let's get to coding. Okay, now let's get started with coding. This is the exciting bit. We're going to have 2 pointers, slow and fast. These 2 pointers are going to be initialized to head. Why is that? Because we want to check if there is a cycle. And we're going to have a Boolean variable called isCycle. And we're going to start out with this Boolean value as false. And the reason for that is because we're going to use that to register whether or not we've had a cycle in our program thus far. Let's go ahead and try to look for a cycle. So while fast is not none, and fast.next is not none. By the way, if you were asking yourself why do we have isFast and isFast.next is none, it's because there is no next for a none type, and that's going to be an error that we're going to have if we don't do this. Anyway, let's move on. So slow is only going to take 1 step, slow.next, and fast is only going to take 2 steps because it is the fast one after all. If slow is equal to fast, then in this case we've had the cycle, right? Which means we could register the cycle here, right, as true. This is better for bookkeeping and all. Now, this is the first step of our process. Remember from the board. Let's get now the cycle. So length of the cycle is going to be equal to getLen function. I'm using this getLen function just to not have this place crowded. We're going to define this soon. I'm just going through the process we discussed on the whiteboard. And then we're going to try to get the starting node. So get node. Okay? Once we get the starting node, which is what we really want, we're simply going to break because we no longer need to loop anymore. We found the cycle, we found the starting node. Nothing needs to be done. And then enter, return the starting node only if it is a cycle. And the good thing is we have a variable here, a Boolean variable that checks for that. Else, none. With this logic, we're done, right? But we need to implement these two, getLen and getNode. So let's go on and build this. Let's give ourselves some room here. And let's backspace all the way back so it doesn't be inside the class. Anyway, so let's begin by thinking about which parameters are we going to pass for the getLen. Well, it's clear that we're going to pass one of the 2 pointers, right? The slow and the fast. Well, it doesn't really matter because they're both at the same point, so we can just simply pass either of them, right? For the getLen. And why are we passing the slow and not the head? Well, to answer that question, because we want to know how long is the cycle, right? So we're going to pass something within the cycle. So slow, while, let's make another pointer. Pointer 2. Okay, and it's going to start out from the same location as slow. While pointer 2 is not none. Well, let's make it just while true because is not none doesn't make much sense, right? So pointer 2 is going to be equal to pointer 2.next. If pointer 2 spins all the way back and touches base with the slow pointer, then the cycle is over, right? So break. But we need to register the length of the cycle. So we're going to add a variable here called cycle. And with every step that pointer takes, it's going to take a step of its own. Right? So once we're done with everything, it is simply going to return that cycle. The good thing is that this function only does one thing, which is return the length of the cycle. So think about this, right? We are at a starting point with the pointer, and then we go a step further, and then another step further, and so on and so on. And we register the cycle meanwhile. Once they touch base, that means that the cycle has been complete. So we return that. Okay. Now let's get the node. The node here is a bit different, right? Because we have the information that we got from the length of the cycle. So we're going to pass that in here. But we're also not going to start from slow or fast, right? We were going to start at the beginning, from head. So we're going to pass in head here. And we're going to create our own new little slow and fast pointers. They're both going to start at head. The only difference is that the fast pointer is going to get a head start. So while, wait, let me pass in the cycle variable here as well. So while cycle is larger than 0, then move the pointer fast.next, and then subtract 1 from the cycle. That way, we can give it the head start. So if it's 5 steps ahead, it's 5 steps ahead. And these 5 steps represent the length of the cycle that we got from here. Okay? Now, once we're done with this, we can now move both pointers at the same time in the hopes of them meeting once again at the starting position. So let's move on. So while slow does not equal fast, then slow is equal to slow.next, and fast is equal to fast.next. Right? Once we're done with that, we can return either the slow or the fast. It doesn't really matter. They're at the same point. So now you can fit this whole logic, right, in here, and then you get the starting node. Once you have that starting node, you can return it if it is indeed a cycle. Otherwise, just return none, and that's it. Just going to submit, not even going to run it. Right, so there is no cycle. Where? Right, so found the problem. The problem was here. I forgot the not. Anyway, so just let's submit. Okay, let's submit again. Still 58.85. Either way, that runs in O of n, and it doesn't use any auxiliary space, so it's O of 1 space. We're going to be solving a Microsoft interview question. So the question is minimum deletions to make character frequencies unique. Quite a handful of a question name, right? So the question goes as follows. A string is called a good string if there are no two different characters in string S that have the same frequency. Given string S, return the minimum number of characters you need to delete to make S good. Now, the frequency of a character in a string is the number of times it appears in the string. For example, in the string AAB, the frequency of the character A is 2, while the frequency of character B is only 1. Now, let's look at example number 1. For example number 1, we have a string here called AAB. Now, A's frequency is equal to 2. B's frequency is equal to 1. They are different frequencies. Therefore, we don't need to make any deletions of any sort to make them a good, whatever that means, good string, right? So the output is equal to 0. Now let's look at example 2. This is different a bit, right? We have 3 A's, and you have 3 B's and 2 C's. So clearly, because we have 3 A's and 3 B's, this is not right off the bat a good string, whatever that means, right? So we need to make some changes. So we can delete 2 B's, resulting in the good string. Why do we delete 2 B's and not just 1 B? Well, because if we delete 1 B, right, sure, it won't be equal to the number of A's here, like this is going to be 3 and this is going to be 2, but there are 2 B's and there are 2 C's. So we need all the characters to have different frequencies, and this is the issue that we're dealing with. So clearly we need to make some sort of mechanism that doesn't do this process only once. We need this process to recur more than once. Now, I hope this gives you some sort of a hint on what we are going to do. Anyway, in example 3, it pretty much follows the same concept and how we're going to do things. So let's go to our Blackboard really quickly and think about how we're going to do this. Firstly, since this whole problem relies on the frequency of a letter in the string so much, then what we can do is we can make some sort of data structure. Hopefully this data structure would look something like a hash map. And this hash map is simply going to map all the characters to the frequency. So A, for example, is equal to 3, B, there are 1 character, and C has for example, 5 characters, and so on. Right? Once we create this, the problem is a step closer to being solved. By that I mean, we now have our frequencies, and since we have our frequencies, now we're going to make sure that they're all distinct. So the first thing we're going to do is that we're going to pass through this dictionary or hash map. I'm using Python, so dictionary. You can still follow along in a different language. So if you go to the first, let's say B is equal to 3, right? If you go to B, right, and you see that prior to B, there has been a value 3. That means we need to make some changes here. So it's all about discovery. Once we've discovered that there is a previous value that was a duplicate, that means we need to change the current value to 2. Okay, let's say that the C was 2 as well, right? Well, we need to make some changes here, right? To make that into 1. That's basically the idea behind it. I understand a lot of you might be confused at this moment on how to do this exactly in code, so let's start doing exactly that. And get started. First things first, let's build our hash map. So the hash map is going to be the frequency map for all the characters. So it's basically a dictionary. And we need something to keep track of the amount of deletions that we need to have. So we're going to make a counter, right? So let's build the frequency map. And how do we build the frequency map? Like so. For character in S. S refers to the string. If the character is indeed not in the frequency map, then we're simply going to make it exist in the frequency map. So frequency map character is going to be equal to 0. Okay, great. What if it exists? Well, if it exists or didn't exist, we're just simply going to add it after creation. So frequency map char plus equal, sorry, a little bit of C++ there, plus equal to 1. Like that, we've built our hash frequency map. Okay? Now, since we have that, we really have no need for the S anymore, for the whole string anymore, because we have all the unique characters with their values. And since this problem really deals with the values themselves and not the characters, then we really have no use for this anymore. So let's move on. So for character in, this time the frequency map. This is getting all the keys, right? Every key. So this is the character at the moment. And we want the value. Now, while the frequency map character, the current frequency map character, has been seen before, then we need to make some changes, right? Okay, how do we express that in code? It has been seen before. Well, simply we can make a auxiliary list. Let's call it unique. Now, I'm not going to say unique characters. I'm going to say unique values because we're dealing with values. Remember, not characters. We're accessing values. So, while the frequency map character is not, well, is in the unique list, then we need to keep making changes so we can adjust. And what are these changes? Well, basically, we need to make some sort of deletion. So +1, we need to make 1 deletion. Since we did 1 deletion, let's actually perform this deletion. And how do we perform this deletion? Well, we simply reduce the value within the frequency map for that specific character. Okay? So I hope you're following along. Now, once we're done modifying this value for that specific character, now what we need to do is to basically add it to the unique value list, so when we loop again all the way back, it's there. So if the frequency underscore map character, here we're dealing with the value, remember, not in unique value. Then all we need to do is basically append that to that unique value, dot append. Of course, you could have used something like a set just as easily, because it doesn't allow for duplicates. That's completely acceptable. That's completely fine. Just make sure that there are no duplicates. And now we're just going to append that. Once we're done with everything, we're simply going to return the count, total count, right? I hope I didn't make any mistakes here. I don't think I did. Anyway, so this block of code here, this logic deals with building the frequency map. And this utilizes the frequency map to adjust the numbers within it while keeping track of the total number of deletions. Okay, I think I did a mistake here. I made a mistake here. Oh no, I didn't. Oh, I see the problem. Frequency, I forgot when frequency map could be less than 0. So that's really what happened. Let's submit again. Hey, there we go. Works perfectly fine. I'm going to be solving the question, remove duplicates from sorted array. Now, let's read the question. Given an integer arrays called nums, sorted in non-decreasing order fashion, remove the duplicates in place. Now, that's a key word here, in place. That means we can't use any auxiliary data structure, like a list, to store these values and return them, such that each unique element appears only once. The relative order of the elements should be kept the same way. Now, since it is impossible to change the length of the array, in some languages you must instead have the result be placed in the first part of the array's num. More formally, if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. It does not matter what you leave beyond the first k elements. Okay, this is getting interesting. Now return k after placing the final result in the first k slots of nums. Do not allocate, you see, that's what we were talking about. Do not allocate any extra space for another array. You must do this by modifying the input array in place. So they said it twice now, with O of 1 extra memory. Okay. Right, so this is just a lot of mumbo jumbo. Let's go to the examples. So the examples say we have an input 1, 1, 2, and the output is supposed to be 2. Why is that? Because if we remove all the duplicates, what we're left with is really 1 and 2. Now let's look at something larger. So this is an array that has numbers between 0 and 4. There are a lot of duplicates. Once we funnel them down, we get 0, 1, 2, 3, and 4, which is 5. This is really what we need to return. We need to return an integer value with all the number of distinct variables that we have. So let's think about what we need to do in order to remove this. Well, since this is a sorted array, then the first thing we're going to think about is not the sliding window, but in fact the two-pointer method, where we have a pointer somewhere in the array and another pointer in a different place in the array, or in fact the same way, but they move at different speeds, which is exactly what we'll do. So let's solve the question and then break it down a bit. So first, let's say that we have pointer 1. Let's call that pointer I. So pointer 1 starts at 1, and pointer 2 starts at also 1. So what is pointer 1 and what is pointer 2? So pointer 1 is going to be the normal loop. So every loop we're going to have this pointer move at the speed of 1. However, the non-duplicate loop, the non-duplicate pointer's whole goal is to basically only walk as long as there is no duplicates. Once there is a duplicate, it stops in place. It hangs back a bit until this duplicate problem is solved. And this is incredibly important because let's look at an example here. You see this 1 here? This one is positioned very well, but the 2 ones after them, these are the problems. So I could stop here until these 2 issues, these 2 numbers are solved. And that is really what we aim to do. We need to stop here until the other pointer, which is I, moves all the way forward towards 2 or any other number that isn't 1 and fixes the problem here, right? Because we stopped here and we can only move until this issue is fixed. That's really how it's going to be solved. If you don't understand it, maybe watch through the code walkthrough and hopefully you'll understand it. So while I is smaller than the length of the array, here it's called nums. If nums non-duplicate minus 1 does not equal to nums I. I bet right now you get what nums I is, but you don't get why this minus 1 appears to be, right? And the reason for that is, like we just talked, in this example, we're dealing with these 2 1s. Meanwhile, the I pointer is somewhere in front looking for a different value. So really this non-duplicate minus 1 is this value right here, and the non-duplicate is this value right here. Okay, so let's continue. Let's copy this exact same thing and I'll just remove the 1. So if you think about it, although it's not a really good way to think about it, we have 3 pointers. 1 is non-duplicate, and 1 is non-duplicate minus 1, and 1 is the I. Okay? So we're going to shift that number back a bit, because as you remember, nothing after the distinct value matters. And then once the non-duplicate problem is fixed, we can actually move a step further. However, meanwhile, the I walks at a very constant pace. It doesn't matter if there's a duplicate, no duplicates, doesn't really matter. So once all of that is over, we will find ourselves with the last step of the non-duplicate at the end of all the distinct numbers. And that really is the count of all the distinct numbers. So what we can do is simply return the non_duplicate, because this pointer points here now. So you see all of this, it ignores all of these parts, but only points here. So I can simply just return this. Okay, now the problem solves. We are going to be solving a question called reorder list. Now this is a linked list question of medium level of difficulty in Leetcode. Now the question goes as follows. You're given the head of a linked list. The list can be represented as L0, L1, Ln-1, Ln. Now the reorder list is supposed to be L0, Ln, L1, Ln-1, L2, Ln-2. Now of course this probably doesn't make much sense to you right now, but yeah, that's usually how Leetcode questions go. Now let's look at the examples. Example 1 says we have a list 1, 2, 3, 4, and we want to change it to this format, 1, 4, 2, and 3. So let's look at the pattern. What happened here? It says 1 is 1, and then the second part is the last element in the previous linked list, and then the third element is the second element here, and the last element is the 3. So we can see that there's a bit of a pattern here. We're having 2 pointers, one at the beginning and one at the end, and they're just being combined into that format. So let's go back to our reordered list here, L0, Ln. So one from the back, one from the front, one from the back, one from the front, and so on and so forth. So I guess it makes sense. Let's look at another example. So this is going to be 1. Then let's take one from the back, which is 5. So we have the 5 here. And then let's take 2. Let's take from the other side 4. And then let's take whatever's left here, right? 3. So it seems like this linked list is being split into 2 halves, right? And we're just getting from each half 1 node. And we're filling it up as we go. That's basically what is going on here. Let's solve this question. Let's go to our blackboard and solve this question. So this is the plan of attack. Since it's basically 2 halves, right? Then what we're going to do first is that we're going to find the center so we can in order to split it in half, like so. And after we find the center, we need to think about how we can do that process where we get from the front and then go back a step. You see, in linked lists, we can't do that unless it's a doubly linked list. We can't do that in a singly linked list. We can do that in an array, and it would be very trivial, but we can't do that in a singly linked list. So what do? Well, we simply reverse this. Because at the end of the day, right, if we're going to do this and go backwards, then it's the same as 4, 3, and going forwards, right? Taking a step forward. So that's really what we're going to do. The first thing that we're going to do is basically split this. And once we have the 2 halves, we're going to leave the first one as it is. And then the second one, we're going to reverse it in such a way that we can traverse it at the same time. Once that's done, once we have 1, 2, 4, 3, now we can have 2 pointers. 1 pointer here and 1 pointer here. And then we can add as we go. So 1, and then we can take from the front 4. And then we can move these 2 forward. And then we take 2, and then we can take from the front 4, which, surprise, surprise, is the same answer as the guide answer. So that's the step. Step 2, find the center, reverse everything around, and move them together and combine them. Brilliant. So this is the plan of attack. Each one of those steps, I'm going to make it into its own function, so there would not be any sort of confusion. Okay, first, let's find the center. So for the center, I've explained this technique before. It's called the hare and the tortoise. I'm going to do the following. Find center. I'm going to have 2 pointers. One is slow and one is fast. And the fast pointer is going to move at twice the speed of the slow pointer. By the time the fast pointer reaches the end of the array, we will have our slow pointer at the middle of the array. Hence, that's why one is double the speed of the other. Anyway, so while fast is not none, and fast dot next is not none. Okay, slow is equal to slow dot next. It's moving at the speed of 1. This is the tortoise. And fast is equal to fast dot next dot next. If you don't understand what's going on here, please review the video linked list with Captain America. This is going to help a lot. Anyway, so now that we're done with this, all we have to do is just simply return slow, because this is the location of the middle node, and that way we found the center. So we've successfully finished the first step in this. Now let's move on to the second step. So the second step says the following. We need to reverse it. Well, how do you reverse a linked list in general? That's really the question. Well, we reverse it like so. We have a previous pointer, which is going to be none. And then we have a current pointer, which is going to be equal to head, beginning of the linked list. While current is not none, what's going to happen is we're going to store the next step, because once we flip things around, the pointer is going to lose all sense of its identity in some sense. So we need to store the next step for the current .next. Okay? So yeah, here we're just storing that step. Now, current.next is equal to prev, previous. This changes things. Now the current.next is actually pointing to something else, right? Anyway, finally, once that is done, all we have to do is just move the 2 pointers ahead. So previous is going to be equal to the current state, and the current is going to be equal to next. So anyway, let's recap really quickly. This stores the next step because we don't want to lose the information about what's next on the list before we actually start. And this does the switch, so now it points backwards instead of forwards. So if the dot, remember this, if the dot next is before the equal sign, that means we are actually changing what we're pointing at. So now we're switching and pointing backwards instead of forward. Switching back. And this one, we're simply moving the pointer forward for the previous, right? We're making the previous now the current node. And this one, we're just getting what we stored here, the current.next, which is the next step in the linked list. If you don't understand this, please write it out on the blackboard. It helps a lot. And remember that when the dot next is after the equal sign, it's completely different from when the dot next is before the equal sign. I mean, at least the conceptual idea of it, okay? Anyway, so when you're done, you return prev and not the current head, because the current head at this point would be none, right? By the end of it will be none. So you want what's before the none. You want the prev, okay? So now we have the 2 functions, the 2 steps. We need the third and last step. And the last step will be basically to combine everything together. Sorry about that. Anyway, so center. So I'm going to say first half is going to start from, well, basically the head. And the second half is going to start from, let's say, find center. And let's pass in head. And since we want it to be reversed anyway, so let's just do it while we'll add it and not make it a separate step of its own. So the center here starts at the reversed center of the second half. I hope you get this. Okay? So now we can combine things together. While first underscore half is not none, and second underscore half is also not none, then what we want to do here is basically flip things around a bit. So next is equal to first underscore half, right, dot next. Remember, we're using the same logic as this, right? We're storing something for the next step so we don't lose the identity of what it is. Anyway, and now the first half dot next is going to be equal to what? Think about this, right? I know the answer, but I'm telling you to think about this, because when the dot next is before the equal sign, now we're pointing towards something, right? So what are we going to be pointing on? Well, we're going to be pointing to the end, right? So the 1 is going to be pointing to the 4. And the 4 is in the territory of what? The second half. And the second half is reversed, right? So the 4 is in here, like in this spot, and the spot of the 3. So really, we're pointing to the first element in the second half. I hope you get that part. Now we're done with this part, and we want to move the pointer forward. First half is going to be equal to nxt. Now we're going to do the same thing for the second half. Same idea, same concept. So nxt is going to be equal to the second half dot next. And now the second half dot next is going to be equal to what? Remember, the second half dot next here is still the number 4. So it's not enough that 1 would point to 4. 4 needs to point to 2. 1 points to 4 and 4 points to 2. So we're going to need to actually do this. So second half dot next is equal to first underscore half. And then we're going to move the second half forward a step, which is the NXT that was already stored. Once we're done with all of this, all we have to do is just check for the final node if first underscore half is not none. Then what we do is we basically add a none, right? And that's really it. That's the question. So now return hit. Let's run this. Hopefully we didn't miss anything. These type of things are usually hard to debug. Okay, our return is outside the function. Oh, well that's not too bad. Wait, can't see like that. Let me zoom out a bit. Oh yeah, there we go. Let's see. Hey, there we go. Let's submit. Did we get away with it? Yeah. Anyway, so that's the question for you. It's basically a 3-parter. We find the center, reverse the last bit. After we reverse the last bit, we combine them together like so. Right? This piece of logic is repeated twice. It's very important to look at what we're pointing at. If the dot next is before the equal sign, it's completely different from when the dot next is after the equal sign. That's a very important distinction to know, because if you're solving the linked list questions, and you're a beginner, this will confuse you. So anyway, good luck. If you have any questions, please leave them in the comments. I'd be happy to help. Just let me know. I'm going to be answering a very easy question. I think you'll like it. It's called reverse a string. And the question is what you might expect. Write a function that reverses a string. The input string is given as an array of characters S. Now, it's very important to note here that you can solve this question quite easily using the reverse function, .reverse. But in an interview setting, that's not what they would want from you. They would want for you to build that reverse setting, right? Not to use the pre-defined functions. Now, let's look at how that would work. So the input is a character array, not a full-on string. And the output is simply the reverse of that, but also in an array. Now, we'll solve this question using 2 ways. The first way is going to be using the iterative method, and the second will be using a recursive method. So let's start with the first one. So this is going to be the 2-pointer method, right? Where the left, there's going to be a left pointer that starts at the beginning of the array, and there's going to be a right pointer that starts at the end of the array. So it's going to be at the end of the array here. So while the left pointer is smaller than the right pointer, then what you need to do is simply swap the values, right? And then move the pointer forward if it's the left pointer. But if it's the right pointer, then move it backwards. Once you're done with everything, simply return the new array. So let's build the swap function out really quickly. So def swap, and you take as input the actual array, and you take in the left pointer and the right pointer. Let's give ourselves some room. Okay, we are going to swap the left with the right. This is the Pythonic way of doing things. You can do this in your native language using an extra variable called temp, but this is completely fine. And since we're defining this function inside the class solution, then we could simply add the self here, and we could use the self here. Now, let's pass in the variables. So they're named exactly as in the function, so it shouldn't be an issue to track. And basically, that's it. So now let's have a look. There's going to be an issue here, right? Which is, some of you might be thinking, why is this working? Why is this working? Well, it's simply because of the left smaller than the right thing. If the left was not smaller than the right, then as soon as the right crosses the boundaries into the left territory and the left crosses into the right territory, things are going to be reversed back to the way they were. So that's why left is smaller than right. Okay, let's submit this. And it's all good. Now let's solve this in a recursive way. Okay, now let's solve it recursively. So for the recursive method, it's going to be the same logic, just simply using a different method called reverse string helper. Okay, it's going to we're going to have an argument self because we're going to define this function within the confounds of the class solution, and then we're going to have s, I, and n. S is going to be the actual array, and let's change I to left and n to right. Okay. Now, let's move on to the actual code. So left is going to start out as 0, and right is going to start out at the length of the array, -1, which is the last index. And finally, we're going to use this recursive function within this main function. Okay? Now, let's define this long-awaited string helper function. So we're going to do that such that it would change in place. So if the left this time is greater than the right, so notice that we switch things around because the base case is usually the opposite. So we're going to return s, okay? But let's first define s. Well, s is going to be simply the swapped version of the previous s. So s left, s right is equal to s right, s left. And finally, we're going to recursively iterate through this again. Only this time we'll pass different values. So this is going to be +1, and this is going to be -1. Let's run this. And it runs successfully. And that's it. Let's hope it works. Hey, there we go. This video we're going to be solving a question called sort colors. This is a medium question level of difficulty on Leetcode. Let's read the question. Given an array nums and an object colored red, white, or blue, sort them in place so that the objects of the same color are adjacent, with the colors in order red, white, and blue. We will use the integers 0, 1, and 2 to represent the color red, white, and blue. So basically we can just simply ignore this whole format, red, white, and blue, and really focus on 0, 1, and 2. So we want just simply an ascending sort. That's what it seems to be. Now, you must solve this problem without using the library's sort function. So basically without really doing this. Return nums.sort. If we submit this, this works. But there are two problems with this. Look at how fast this is. 8.10%. Right? So even if your interviewer does allow you to do this, you might not necessarily want to do this because it's extremely slow. Because after all, this is the complexity of this is n log n. So there must be a better way to solve this. Let's look at the input first. The input is an array filled with 2s, 0s, and 1s. Nothing else. So there is no some weird input that we don't know. And the constraints is basically tell you don't do anything crazy. That's all it says. Let's look at how we're going to solve this question in our methodology here. So this is the input array. And here, we're going to create 3 pointers. Pointer 1, we're going to call it low. And pointer 2, we're going to call it high. And pointer 3, we're going to call it I. Now, what are these pointers? Well, this pointer is just simply going to loop through the array at a specific pace. And these two are going to be used for replacement. This is going to be placed at the end of the array. This is going to be placed at the beginning of the array. This is going to be in charge of all the small numbers. And this is going to be in charge of all of the big numbers. What are the small numbers and the big numbers? Well, the small number is 0, and the big number is 2. And the 1 is simply in the middle, so we don't really need to worry about that all that much. So let's put our pointers. Low, high, and the I pointer. This is their starting point. If you look at the I, right, let's just move it a step further so we can actually do anything with it. Right? If we look at the I in this case is equal to 0. So, since this is the smallest number possible, we're simply going to shift that with the low pointer because it's used for replacement. So it's going to be 0 and 2, right? And then we're going to move this I pointer forward, like so. So we find here that the current number is actually 2. So this is the highest number possible. And what pointer is in charge of the highest number possible? Well, it's simple. The high pointer. So we're going to look at I and H. I'm going to replace their positions. So this is going to be 0. And this is going to be 2. And then we're going to keep moving the I forward, right? As long as this works. The reason why we're not worrying about the 1 so much because it's going to fall naturally into place as long as we're sorting the 0s and the 2s. The 1s are simply going to follow in place. Now let's look at this in code because some people understand better in code. Okay. Here we have our editor. Let's remove this now. We no longer need to sort in n log n. We can simply sort in n. So we have our I pointer, our low pointer, our high pointer, right? The first one is going to be 0, and the second one is also going to start from 0. And the last one is going to be at the end of the array, so lennums minus 1. While I, because that's the pointer that we really want to iterate through, is smaller than high, because remember, high keeps going back. So while I is smaller than high, we are going to be looking at 2 states. The first one, if the current nums, I, is equal to 0. This is the smallest number possible. So let's look at the pointer that is responsible for the smallest numbers. Well, that is the low. We're going to swap nums I with nums low, like so. Nums low and nums I. If you do it differently in your own programming language, that's completely fine. This is the Pythonic way of doing it. Now elif, right? Nums I is going to be equal to 2. We're going to do the exact same thing, just with the high pointer, right? Now, if you've been paying attention, we did not move the pointers forward. So let's do that. Let's think about how we could do that. Well, in this case, we already put the new number, which is 0, at the very beginning. And we know that whatever the upcoming number is, it's definitely not going to be that big of an issue. So we can simply move the I plus is equal to 1, right? We're going to move the I pointer forward. And we're also going to move the low pointer forward because it has been adjusted. As for the 2, what we're going to do is simply just decrement the high pointer backwards. But we're not going to move the I pointer forward. And the reason for that is because we don't know if the the new number that was placed in the middle, because remember, we're swapping. Yes, the 2 is being thrown all the way to the end of the array, but there could be a 0 in the middle of the array. So we might want to swap that backwards. So we're not going to push the I forward. We're only going to push the high pointer backwards. If, on the other hand, it was equal to 1, we're just simply going to move the I forward. Now, once that is over, once that's done, what we can do here is simply return the nums. And the reason for that is because everything here has been done in place. Nothing has been done, by copy. And this runs. Let's submit. Okay. So you see the difference now in speed? Now I know the Leetcode runtime counter isn't exactly the best, but it definitely shows like this is a huge leap from 8% to 75%. And the reason for that is because this is asymptotically equivalent of O of n. Going to the answer to the question, squares of a sorted array. Now this question goes as follows. Given an integer, array nums, sorted in non-decreasing order, so ascending, return an array of the squares of each number, sorted in non-decreasing order. And the first example would be that we're given this array, -4, -1, 0, 3, and 10, and then we square every last one of them, so the -4 becomes 16, the 1 becomes 1, the 0 becomes 0, the 3 becomes 9, 10 becomes 100, and then we would have it in a proper ascending order. In the example number 2, it's not very different. It has a mix of both negative numbers and positive numbers, and we do the exact same thing. So if this question didn't have negative numbers, it would have probably been very trivial. But due to the fact that it has negative numbers, it needs a little bit of thought. Well, one bad solution to this is that we could loop through every single number, and then square every single number. And then finally, we would use the sort method. Once we use the sort method, we could return the value back, and then we would have everything going perfectly well. So let's submit and see how that would work. Okay, there is a problem here, that this runs in big O of n log n. And the optimal solution for this is big O of n. And that's what they would probably be expecting of you in an interview setting. So n log n is not what we want. We want big O of n. So let's restart this, and let's tackle this in a different way. All right, so let's try solving this question. So we have the array, -4 and -1, 0, 3, and 10. What we can do here is use the two-pointer technique. The two-pointer technique basically says that we can use two pointers to point at any two random values, well, not really random, it depends on the situation, and then we would move them either at different speeds or at different times. So here I'm going to have one pointer pointing to the beginning of the array. I'm going to call that the left pointer. And then I'm going to have another pointer pointing at the end of the array. Why? Because the ends of the array, whether it's the beginning or the end, are sure to give me the biggest value. Okay, so I would have another array here, which is empty, only initialized by zeros, okay, that has the same length as this array. So -4, -1, 0, 3, and 10, that's 5 zeros. So 0 and 0 and another 0. Okay, so the way that that will go is basically we ask ourselves if the 10 or the -4 square is bigger. So in this case, the square of 10 is bigger. So we would choose to put the 100, which is the square of 10, at the end of this array. Then now that that's done, we move the pointer backwards at number 3. So we have right here. Once we compare between -4 and 3, and we find out that the square of -4 is actually larger than the square of 3, we would say that the next value that we should put here would be 14 instead of this 0. And we would move this left pointer right. Okay? Then we would do the same process over and over and over again until the left pointer is smaller than or equal to the right pointer. That's basically how it works. Let's get right into the code. Alright, so let's code what we just set out. Okay, so left, we're going to have the length of the array as len nums, and then we're going to create a empty list that has all zeros of length n. Okay, I could have just as easily created that with a loop, but I choose to write it that way. And we're going to have 2 pointers left and right. The first one is going to be 0. The second one is going to be at len n. At n minus 1 because n is already the length. So while the left pointer is smaller than or equal, and the reason why it's equal because if we have, an even number of numbers inside the nums list or an odd number, so we can cover for both cases. Okay, so left smaller than or equal to right. Let's get the left value, and let's get the right value. So the left value would be nums, and then left pointer power 2. The right value, on the other hand, would be equal to nums right also power 2. So there's 2 situations here. One where the left value is smaller than or equal to the right value. Okay. In that case, all we have to do is basically fill up that square list from the end to back. So for that, I'm going to create its own pointer. I'm going to call it the filler pointer because that's the one that iterates in that specific list backwards. So I'm going to say that it's going to be n minus 1. Okay, so if that's the case, then all I have to do is basically squared filler pointer, and this is going to be equal to the right value. Now that we attained that right value, all we have to do is just simply push the right pointer backwards. Once we've done that, we move to the next situation, which is the opposite. If the right value, let's just keep it the same manner. If the right value is in fact larger than, if the left value is in fact larger than the right value. So we get the squared and we get the filler pointer to also help with the filling. So lift, so the left value is going to be inserted. Once that's done, we are going to right, left, -1. Okay, so we're gonna add 1. We're gonna push it forward. So here we're pushing it forward, and here we're pushing it backwards. That's really what's going on. So now that we filled things up in both cases, we're just going to push the filler pointer backwards. So now that we have everything done and everything's filled up after the while loop, what we can do is return the squared list. Okay, so now let's see the difference. There we go. So everything's working fine. Don't worry about this number that it's actually lower than what we've seen before, because in every submission, for whatever reason, it has a different number. So for example, if we submit again, it's a different number, 46. So trust your own reasoning, trust your own judgment when you're looking at these things, because we know for a fact that this is O of n and not n log n. Also, for the space complexity, this is O of n because we're filling up the squared, right? Where n is the number of values in the length. I'm going to be answering a question called subarray product less than k. Now, this question is a simple question in theory, but once you get started with solving it, you'll find that there is a few problems with it, right? Now, let's start with this question. Given an array of integers, nums, and an integer, k, return the number of contiguous subarrays where the product of all the elements in the subarray is strictly less than k. So let's first define what a subarray is. A subarray is just simply a part of the array that is after each other or a singular value in that array. So for example, 10 and 5 is a subarray. 5 on its own is its own subarray. So you see how this is going, right? Now, the number of values that we need here are the numbers of values representing the subarray, all the possible subarrays that are strictly less than k. So 10 is strictly less than k because 10 multiplied by 1 is 100. 10 multiplied by 5 is less than 100, it's 50. And 5 on its own is less than 100. And 2 on its own is less than 100. And 2 multiplied by 5 is less than 100, and so on and so forth. Now, the idea here is not to get all these subarrays, which is quite the relief, but we need to get all the possible ways we can get that. Now, let's see how we could solve that question. The method I'm going to be using here is a sliding window technique, where we start with a window start. The window start represents the beginning of the window, and a window end. The window end is simply the iterator in a for loop, so it just goes at a constant pace of 1 per loop. And it starts out at the same position as the window start. Now the idea here is to use that window end to check the current value. So the current value is 10. If that current value is in fact smaller than the value k, of course this is multiplied by 1, or the cumulative product, which is product is equal to 1 multiplied by whatever the number is, right? So 1 multiplied by k by 10 is smaller than k. And then we move on to the next value, which is this one. So window end here again. And if we multiply this 10 multiplied by 5, we will see that this is 50, and it is indeed smaller than k. Now, as soon as we hit that last one, right, we see that 10 multiplied by 5 multiplied by 2 is 100. And this is not strictly less than k. So the only thing we can do here is basically make this window a little bit smaller. So we just move this part here to maybe here, a step further, and then we check once more. Is 5 multiplied by only 2 smaller than k? Yes, indeed. So that means we have another subarray. But the thing is, this subarray has smaller subarrays, like we discussed, 5 and 2. And that is the whole trick. So the idea here is to have a window that keeps moving and only shrinks when the rules are no longer applied. And when the rules are no longer applied, we can start counting how much are we left with. Once that happens, we can simply, at the end of it all, return the value. Let's see this in code, because I know a lot of you understand better in code. Okay, so window start is going to be equal to 0, and also the total sum of all the possible array, the total count, is going to be equal to 0. So both of them are going to be starting at 0. But this is the 0th index, and this is the number of total subarrays. Now, let's move on. The product, or rather the running product, is going to be equal to 1, so we can use it in our calculations. So for window end, in range len nums. Now the current value is going to be equal to nums in that index. So now we're going to calculate that product, that new product multiplied by the current value. If you think about it, this is really 10 multiplied by 1, if we're going stepwise. Now, while, and the reason I'm saying while here and not if, is because we're going to need to do this over and over again. We're going to need to shrink it not just once, but a couple of times. So we're going to shrink it here as soon as the rules don't apply. So while the product is larger than k, as long as the rules don't apply, and the window start is smaller than the window end, then there is something we can do. So the first part of this Boolean value here is basically saying, do the rules still apply? Well, there are two answers to that, yes or no. And the other one is saying, are we done with the whole array? Anyway, let's move on. So as long as it's bigger, then what we can do is reverse that multiplication that we did earlier, like so. Current underscore value, no. We're not going to do that because the current underscore value is at the window end. What we want is at the very beginning of the window. Remember this part here. We want to remove the 10 rather. So nums and then window start and not window end, because we're shrinking from the left side. And this is the actual step of shrinking, the window start plus 1. This is simply making our indicator here, the product value, lose that value at the beginning of the array. Now, once we're done with all of that, that means we're left with a subarray that contains all the other subarrays that have a value that is strictly smaller. So the answer is going to be total underscore count plus equal to the window end minus the window start plus 1. Now this plus 1 is because of the actual subarray itself, the full subarray, the 10 and the 5. The window end minus the window start is basically to signify that we have a 10 and a 5. So that's the whole idea, right? Anyway, I missed the equal here because the rules are broken when it's larger or equal, not just if it's larger. Once that is over, we are simply going to return the total underscore count. Okay, so this is registering the amount of subarrays, including the larger overarching subarray. And this is simply so we can have some sort of indicator to when we can decrement our window size or shrink it. Now we're going to run this, and it runs perfectly fine. Let's submit. And there was an issue here. Do you think you can figure that issue out? Think about this for a moment. Why is the expected value here 0? Because if there is an edge case where if k is smaller than or equal to 1. If that is true, then we're simply going to return 0. And that is the only situation where this would happen. So let's submit. And it works. I'm going to be discussing perhaps one of the most famous questions you'll ever find. It's called the two-sum. This is labeled as an easy question, although I don't really know if it's easy or medium, just labeled so. And it says, given an array of integers called nums and an integer called target, return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution. and you may not use the same element twice. You can return the answer in any order you want. Okay, so let's have an example here. We have an array called nums that has 2, 7, 11, and 15, and the target is 9. So just by looking, what we should add to get the 9 is 2 and 7, which is at index 0 and 1. Example 2. We have an array called nums 3, 2, 4, and the target 6. So just by looking, it's 2 and 4. And if it's 2 and 4, then the indices are 1 and 2. And then the next one is nums, then return 6. That's basically it. That's the question. This is the idea. Looks simple, but can you solve it? Right, so let's solve this question. We solve this question by simply creating a hash map. This hash map will have all the numbers that we've seen before. And if we did see it, then we'll simply return the index that is associated with it. So this hash map will store the number alongside with the index that is associated with this number, right? So let's loop through all the numbers one by one. So for index in range len nums. So the current number is going to be equal to nums idx. If the target number subtracted by the number is in the scene, if the difference between these two has been seen before, then we've successfully found two matching pairs because we already have one component of that, and we're looking for the other component, which is target minus number. And if we do find it inside of scene, then we've simply hit jackpot because we have number and target minus number. So if that is the case, what we'll do is that we'll simply return both numbers. However, there is a caveat here, because if we return both numbers, the answer will be incorrect because we need the indices specifically. And to return those indices, I'll simply take the current index for this number, and I will also get the index, but this time from the actual map. Because remember, this hash map works for two reasons: to check if we've seen that number before, and to store the index. That way, whenever we come across that value, we can just simply look it up. So scene and target minus number. This should show the index required. Once that's done, we can simply return. But we're not done just yet. So what happens if the target minus number is not in scene? Well, that's easy. We simply just store the current index and make it equal to the index. This is effectively done. We're effectively done with the code. However, there is a situation where we really don't find anything, so we'll just return nothing. Let's submit. And it works quite well, quite fine. This code runs in O of n, and it also runs in space complexity, I think, yeah, O of n as well. Because you fill up the scene and scene hash map, and this is the auxiliary data structure that you're going to be using, and it could be filled up till the end, where n is the number of numbers inside the nums array. That's it.